Hi, I'm Prab Gauri Shankran, VP of Engineering and Strategy at Performance Motion Devices. We'll talk about motor drive design, tips and trends and tricks, especially for the high performance automation robotics equipment. With that, let's get started. So just a quick background on Performance Motion Devices, PMD. So we've been around for over 25 years. We obviously control over 6.5 million motors worldwide. We do a wide range of products from ICs to amplifiers to digital drives and boards. What we are known for is the C motion language, which is standard C, and it's easy for people to get going with any of the designs. And the same code can be migrated across products. And we have over 1,000 OEMs that rely on PMD products. So our key value proposition is we kind of try to provide plug and play motion control. So it simplifies your product development and gets you to market quicker. We try to provide end-to-end motion control solutions so you can start off with boards, and as the volumes go up, switch over to ICs for high volume applications. We are known for the advanced motion control techniques, and we become a long-term trusted motion control partner. So we have a ton of robotics, automation, and medical companies where motion control is not their core strength, that rely on us to solve all their motion control problems. So this is just a quote from one of our customers, Chai, a founder from Trust Automation. So his point was, the main thing is we could get to market faster because it helped them focus on the areas that they are good at. And they were able to leverage a lot of the advanced motion control stuff that comes with our C motion and the products. So just to dive in deeper, so the trend nowadays is small and portable. So let's just take a look at what the key design considerations are. So the key saying is the size should not affect efficiency. As you can see, the end products from the OEMs are shrinking, and they still want to be able to have the high performance and be able to carry high payloads. So the considerations that come into play, that the three key vectors are the weight of the motion control solution, the power, and the heat dissipation. So those are the three key areas that we would focus on in this presentation to try and see how we can kind of solve all three pain points. So from what attributes to all three of those problem areas are, obviously when you are trying to move something, you have a motor, you have the controls, you have a motion control drive, and you have the algorithm. So we'll try and look through all three aspects to see how we can help get us better weight, size, and performance. So just a quick background on motors. I'm sure a lot of you know about this, but it's always good to step back and take a look at some of the main motors that people use. And as you can see, the type of motor impacts the weight and the torque. So if you can see on the right, you have the brushless DC servo motors, obviously provide the best power to weight ratio, as you can see in the chart on the right. But interestingly, if you look at the torque to weight ratio, the step motors, which are cheaper and lighter, can get to similar or better performance when you run them in what is called a closed loop stepper operation. So we'll dive a little bit more into what closed loop stepper is, but that's an interesting trend that we're seeing, that more and more higher end applications are starting to use cheaper step motors with an encoder to get to similar or better torque to weight performance. So let's take a look at the motors and the control techniques that you can use to improve performance. So as you can see in this slide, we kind of show a difference between open loop, a traditional way you control a step motor, and advanced closed loop step motor operation. So in a traditional open loop, the problem you have is there's these micro steps, and you have a little bit of higher noise, and there's an instability at certain regions, and that causes lower torque output, and there's a higher heat generation. So with the newer closed loop technique, you get to better torque, and you also get to quieter and better thermal efficiency. And the technique is more where you take a traditional step motor, you add an encoder, and you use advanced motion control techniques to kind of close the loop, and use it like a two-phase brushless. So just a background on a traditional step motor, right? As the chart shows in the right, when you move between steps, traditionally the motor tries to stabilize at the bottom of the trough, which is where the equilibrium forces are. So they kind of oscillate at the bottom and then come to rest at the bottom of the trough. So this is, you get this asymptomatic resonance. And as then what you see is it'll go in steps, right? So you'll get to the bottom of the trough. When you make a motion, it moves up and comes back and stabilizes again at the next trough. So that's a traditional step motor and how it reacts. So with the closed loop stepper that we were talking about, you're able to operate it at a more premium, more stable operation point, because you're closing the loop with an encoder. And that lets you move it from the bottom of the trough to an optimal operating point. And that kind of gets you the less heat and lower noise and better performance. And as the trend with these step motors, they're getting smaller and smaller. And as you get to tiny rotors, some of these servo techniques with the closed loop can get you to dampen resonance and get to better position accuracy with these encoders, because you're starting to see smaller step motors being used in more critical high performance positioning applications. And having a encoder to close the loop really helps in those cases. And just a quick high-level background on the closed-loop stepper. So as you can see, you're controlling on the right. You control a step motor with an add a position encoder. So this shows a PID loop where you have the proportional integral and derivative terms, and you're running it like a two-phase brushless, and you have current control. So this applying an FOC technique and kind of a servo commutation function onto a step motor gets you that higher performance. Obviously, we cannot not talk about the mighty brushless DC motor. That's the hallmark of high-end performance. You get the higher torque to weight ratio and the better efficiency. And as you can see, the size has been scaled down. Even the brushless DC motors are getting smaller and smaller, and they're starting to get to higher RPMs. So some of the commutation methods for brushless DC motors, as you can see, a comparison on the right. So you have the sinusoidal, trapezoidal, and the Hall-based commutation. So as you move up the chart, the sinusoidal will get you a smoother performance and a better motion, and avoids the bumpiness of the Hall transition points. So depending on the end system design, you can pick the type of commutation that you want to use. Typically, you use the sinusoidal to get a smoother, higher performance out of your motor. And just a background on some of the advanced techniques that we do in the PMD products is one is this FOC, field-oriented control, where you get a closed loop current control. And this kind of gives you a quick high-level overview of it. So you have the current feedback from sensors on leg current sensing, and then you apply the PI filters, and then you control the motor out of it. So this gets you operating at the right operating point and gets you higher efficiencies. The other thing we see is the higher PWM rates. Traditionally, motors have been controlled at the 20 kilohertz PWMs, but we support all the way up to 120 kilohertz PWM. And so it helps minimize the switching noise and gets you more accurate positioning. And especially for low inductance motors, the higher PWM rates are very beneficial. So with that said, in terms of the motors and the control techniques, let's switch gears and try and take a look at some of the advanced encoders that are being used in these applications. So one common high-end application use case is the SineCosine encoder, where it's a signal format rather than a type of a specific encoder. You can take a traditional encoder and add a SineCosine stage to it and get you SineCosine outputs. Traditionally, the electronics and the chips were not able to process the amount of manipulation that had to be done to get to exact position. But with the advancements in just cell phones and all that, we are able to benefit from that in the motion control world. And now some of the processors and the DSPs can, like the PMD chips, can kind of process that high interpolation rate and do sine cosine encoders native to some of the drives. And this is a little bit more detail on how the sine cosine encoders work. So you have analog inputs, and then you run through a transform, an artan, and a correction table, and you do some interpolation, which is where you need some extra logic to get to the interpolated position. And another trend we're seeing in encoders is these magnetic encoders. The main advantage being they're hermetically sealed, and they are actually pretty high resolution. So, and they're pretty small in size. So we are starting to see, as the motor drives shrink and your end product shrink, there's more and more use of magnetic encoders. So that's a look at all the encoder trends that we are seeing as we go towards making things smaller. But at the core is obviously the motor controller. And we are seeing a trend towards shrinking of the motion controllers. So in this slide, you see on the left, this is actual visual one-to-one size of the product. So the earlier product was done 10 years back. It was a 500-watt motor drive. It's an ion drive, and the new one on the right that we just launched, it's an N-series ion, is, as you can see, it's 1% of the overall weight of the system. It's a lot smaller. It's 37 by 37 by 17 millimeter. And also it's able to put out twice as much power. So in addition to the electronics and the controls shrinking, the efficiency and the performance of these have gone up too. So you kind of see the Moore's law for motion controllers in effect here. So we'll just dive deeper into the new motion controller. It's an integrated all-in-one kind of design. So it's pretty small. It's 1.5 inches by 1.5 inches. So further down in the presentation, you'll see some applications just to get the feel for how small these things are. And they put out 1 kilowatt of power. So it supports a whole wide range of host interfaces, from serial to Ethernet to CAN, and it provides capabilities for advanced control architectures, from hierarchical to flat. And as you can see on the picture, there's a power connector for your high voltage, 12 to 56 volts, and you have the digital signals on the right. So this is a module that can be soldered onto your board. So this is a little bit more detail on this drive. So this obviously supports all of the things we talked about so far. So it does the sine cosine encoder, it does high frequency PWM, and it supports a whole range of host interfaces. And obviously it does a bunch of the safety stuff, where in that case they need 2 separate power supplies. So you have the HV for the high voltage to drive the motor, and you have a separate HV aux supply to kind of keep the controls alive and report back safety and status. And there's a lot that you could do. It has the C-Motion engine where the user can write code to run on the drive for safety or if they want to do a translation from their packet format to a PMD packet format. And we also support BIS and some of the advanced encoder techniques here. So this is just a view of just the capabilities you have. So when you're building a multi-axis system, you could use the same N-series drive, 1 per end axis, and it's a multi-motor controller, and you can support all 3 flavors. So you could pick based on the efficiency you need and the axis that you're supporting. You could have brushless or step motor. Obviously, you could do the closed loop stepper to get the higher efficiency. So it supports a wide range. And then the host protocol can be application specific. So you can write converters for CAN open or EtherCAT. And so it supports both the flat and the hierarchical architecture. So this is just a visual view of how you would use the drive. So this is all the hookups you need. So you have the motor, you have the encoder feedback wired into the drive. You have a bunch of digital IOs to do limits, and you have limits and halls and break. And obviously you have a host interface. And you can do gearing, and you have a second encoder to kind of cam and do gearing functions. So this is one trend. What we are trying to see, what we're seeing is we're introducing this hierarchical architecture. It's pretty common in networking, but we're trying to bring that to the motion control world, where the system host is just talking to one master drive, and the remaining drives, so if, say in this picture it's showing a 3-axis setup, are connected on the back side. So we have a host interface and you have an expansion network. So the host only talks to the master drive and gives it commands, and it's pretty high level commands. It just says, move this axis to this station. And the master drive converts it to PMD commands and provides it over the expansion backside network to the other axes. The advantage for this is it kind of virtualizes the remote drives, and you're talking, it looks like a single multi-axis drive that you're talking to. It minimizes the host code that you have to write, and it kind of moves up the stack in terms of arbitration of creating high-level motion commands that you can send down to the drive. We're seeing a lot of interest in this new path, so that way the key is the host is just talking to one, and we do the magic behind the scenes to address all the virtual multi-axis setups in there. So with that, let's take a quick look at a few application examples that this N-series drive could be used in. So obviously, if you take a traditional robotic arm, if it's a 4 or 6-axis arm, the way we visualize it is you would have one of these N-series drives per axis. The advantage, like we talked about in the previous one, where if you do the hierarchical architecture, at each axis, if you look at the size of it, it's so small, you just have the drive, and all you're providing, wiring across the whole robot is power and your network. So if it's CAN, it's the 2 wires that go across, and power to each of the axes. And the other advantage is for serviceability, you can replace one of these drives in an axis and put a new one in, and it'll automatically assume all the capabilities and functionality and addressing of the old drive. And we kind of auto discover the remote drives in the path and kind of assign the right addresses. So it makes serviceability a lot easier. So what we're trying to show here is what it takes to just control an axis. So it's the N-series controller, a carrier card, and you have some connectors for power and the network connections. So this is, I'd like to see these visuals. It's a lot easier to imagine how I would use these drives. So another application where we want to try and show the scale of it, this is a centrifuge. You can see the N-series drive on the bottom. There's a power supply. And again, it kind of highlights how the centrifuge is built with one of these units. And in this case, it shows an Ethernet connection. And so it gives you a visual view of what these drives look like in terms relative in size to the overall system. The gantry, which is a very, very common application used in 3D printing, automation, lab automation, a lot of different areas. And if you could see on the left, there's 3, this is a centralized architecture where all the controls are laid out together, and then the axis for each of the motors are wired across the gantry. And so you can see on the right, the visual, it's a pretty small board. And all you need is, there's no active components on that board. So you have the 3 drives, you have the connectors for power and network, and that's all you need. And then you wire across these gantries. So this is a pretty convenient use case. And in this case, it shows it's controlling 2 BLDC, brushless DC drive motors and 1 step motor. So you can mix and match the configuration. And the last one we want to kind of highlight is it's like just to show a portable application where you can have a handheld stand, and this is battery operated. These drives consume very low power, and you can have 2 of these control the stand, the 2 motors in there. And this kind of gives you a visual of what that handheld unit would look like. So just to summarize, I know we covered a lot through these slides. So we'll start back. So the key to your end application is you got to pick the right motor for the application, right? Based on the weight, the power, and the efficiency. One trend we're seeing is this closed loop stepper, is where you're able to use a lower end, cheaper, lighter step motor, but get the higher end brushless performance out of it using encoder and some of these advanced motion control techniques. And being able to utilize all the capabilities of advanced motion control with FOC and current control can really increase your efficiency. And towards the end, we looked at how small controllers are becoming more and more common and getting used in portable and wearable motion applications, battery operated situations. And we finally did a deep dive on this N series embedded drive to get you to realize how you can get to market faster. Thank you for listening in. You can reach us at pmdcorp.com. If you have any questions on any of the stuff that was talked about, there's a bunch of white papers and applications on our website. And you can always reach me to talk about anything that we've covered. Thanks a lot for listening in.